Okay, so this week we started our conversation on laminar flow in pipes. And we mentioned that for laminar flow, our viscous forces dominate. And when our viscous forces dominate, then if we have simplified systems such as simple flow in a pipe, then we can pretty much calculate the velocity profile of the flow by solving the Navier-Stokes equations. So we finished off our first class this week by trying to solve for an equation for velocity in a pipe. And then in today's class, we finished solving that equation. So you can see the video with the final solution for the equation. Now that's all nice when we're talking about the laminar flow. However, there's a lot more to fluids than just laminar flow. Most flows that you will find in nature are of a regime called turbulent flows. Now, turbulent flows are these flows where the inertial forces dominate. Because the inertial forces dominate, the velocity profiles are going to be seemingly erratic and chaotic. And when I say chaotic, of course, you can think of the word chaos, and you can think of the word chaos in popular culture, right? Which is just, oh, chaos. But from a physics standpoint, what chaos means is that initial conditions are going to significantly affect final conditions without an obvious or discernible pattern. That doesn't mean that the fluid moves randomly in turbulent flow, but it does mean that the motion of the fluid will seem random from our point of view, because it'll be very hard to deduce the pattern of a moving fluid. Now, if we look at turbulent flow inside a pipe, if I were to ask you to compute the velocity profile of a fluid particle, we're going to have a hard time doing that because, like I said, that motion of fluid particles may seem to be erratic. So you may have different particles moving different directions with different velocities. And you're even going to have streamlines that intersect, right? You're going to have mixing, what's called mixing. So what we're going to do in this class is we're not going to try to focus on determining, right, the velocity profile of each particle, because that's going to take us forever and we may not even get the right answer. Instead, we're going to try to study turbulent flow, how most engineers that deal with general engineered systems, right, so most of the mechanical engineers study turbulent flows, and that is by looking at average values. In other words, instead of looking at the velocity of each individual particle, I could instead try to average the velocity of, let's say, the particles that pass through one section of the pipe, and then use that velocity. So when we're dealing with turbulent flow, particularly for this class, and this is an introductory class, when we're dealing with turbulent flow, we are going to try to deal with average values, average velocities, average pressure gradients, average shear stresses. We're going to have pretty much average values for our study. Now, I promise that after we finish doing all these ordinary differential equations and deriving all these expressions for velocities, that we would start looking into more industry applications. And that's what we're going to start doing today. So today we're going to look at fluids, how we would study them if we were pipe design engineers that work with pipes, let's say for water systems, for wastewater systems, for nuclear cooling systems, for HVAC systems. So any type of piping system that you see in industry. And you'll notice that when we are dealing with the study of flow inside pipes from an engineering perspective, and by the way, when I say engineering, I mean an industry perspective, not a research perspective. So when we're dealing from an industry perspective, you'll note that we pretty much accept the conservation of mass and momentum. And since we're dealing with average values, then we really don't need to, I don't want to say care, but I think that is the right word. We don't need to care too much about mass and momentum because we know mass is conserved. That doesn't really change anything for us. We know momentum is conserved. That's not going to change for us. But we will definitely focus our attention on the study of conservation of energy when we're designing or analyzing piping systems. The conservation of energy is a very important term in piping systems because in the conservation of energy, we will consider all the terms that actually make our fluid flow. So just like when we derived Navier-Stokes equations, we looked at conservation of momentum and we looked at all the forces that acted on the fluid, which made it flow. We're doing a similar analysis with conservation of energy. When we use the energy equation, we look at each of the terms And you'll see that each of the terms is actually going to affect the flow of a fluid. So I want to recall the energy equation, right? This is the equation that we studied several weeks ago. And for the energy equation, remember that we had our pressure, velocity, and kinetic energies for two different points in a control volume. In this case, my control volume is my pipe, or the length of the pipe that I want to study. We mentioned that HP was pump head, HT was turbine head, and HL we mentioned was head loss. In other words, we looked at the energy that we added to a system, removed from a system, and then the energy that we lost. And the focus of today's review session will be that energy that is lost. We want to know how we can quantify that lost energy. Now, again, I talked a little bit about this in our class today, so I'm not going to go into too much detail because you can see the video in the class and understand it a little bit. But just to give a quick recap, that energy that is lost is typically divided into two different terms: a friction term and a component term. So we have a friction term that we call friction loss, or sometimes we call it major loss. And we have a component term. And when I say component, essentially, I mean everything else, everything that's not friction. So a component term is called the component loss, or sometimes called the minor loss. The reason we call the friction loss the major loss and everything else the minor loss is because the friction loss is pretty large compared to the loss from an individual component. In class, we came up with this equation called the Darcy-Weisbach equation. And the Darcy-Weisbach equation essentially gives us the amount of friction loss for a flow. Again, I'm rushing a little bit because we have already covered this in the class, so you will see and with a lot more detail where all these terms are coming from. But for now, what I do want you to know is that Darcy-Weisbach equation does help us to determine the friction loss. This Darcy-Weisbach equation is a function of the length of your pipe, the diameter of the pipe. So if I were to write down my dimensions here, my length would represent the length, the longitudinal length. And then diameter, of course, represents this dimension. And then the velocity head, v squared over 2g. And this is the velocity inside the pipe. So fluid flows inside the pipe with a velocity v. Now remember, we're studying turbulent flow. So that velocity v isn't the velocity of any one particle. It's actually the velocity of, or the average velocity of that flow. And hopefully we'll remember that the average velocity of a flow is calculated by taking the flow rate and dividing it over the area of that flow rate. So we're dealing with essentially simplified terms, right? Average velocity, average pressure, and so on. This F value is called the fanning friction factor. And the friction factor is a dimensionless parameter that helps us quantify the friction. So essentially, it allows us to assign a number to our friction. Now, this friction factor is a function of the regime of the flow, which is quantified by the Reynolds number, and the relative roughness. The Reynolds number, we've already seen this before several weeks ago, is simply velocity times diameter over kinematic viscosity. Let's recall, this is the Greek letter nu, which is the kinematic viscosity. And this kinematic viscosity is just your dynamic or absolute viscosity divided by the density of the fluid. You can find values for different kinematic viscosities of different fluids at different temperatures. Now, this relative roughness term, epsilon over d, essentially represents the ratio of a parameter called the roughness height to the diameter of the pipe. And this roughness height essentially is a measure of the average height of these little ridges that you find if you were to zoom in as much as you can into a pipe. So you know that any material that we're going to zoom into is not really a perfectly smooth material, right? If you zoom in enough, you're going to start to see these little bumps in any material. So that roughness height is an average measure of those bumps. Okay. So that's kind of what we covered today. And I wanted to give you this quick review because I do want to introduce the concept of minor or component losses. Now, we know that head losses are proportional to this velocity head, right? V squared over 2g. So our minor losses or component losses are going to be found by a factor of proportionality and my velocity head. This factor of proportionality, which some books call K and other books call C, is called the minor loss coefficient. And this minor loss coefficient is an empirical value that is measured for different components of a system. When I say component, I mean anything that causes a loss to a system. Does anybody know perhaps any examples of what may cause an energy loss other than friction, right? What else do you think may cause an energy loss in a pipe system? Not just an individual pipe, but a system of pipes. What do you think may cause energy losses? Ryan posted on the chat fittings. That's correct. Ryan, could you explain a little bit more what you mean by fittings for those of us that don't work in the pipe industry?
Yeah, any connection points to pipes, like push to connect fittings or
I like that.
any
Any connection points, right?
angles. Yeah.
Okay. I like that. I like that. Any connections, right? And it's kind of hard to come up with a definition for things that the minor loss coefficient covers because it essentially covers everything except friction. But I think we can not define, but I think we can say that minor losses should cover, among other things, any changes in direction, such as this fitting that changes the direction by 90 degrees. But then they should also cover any changes in geometry. So some examples of changes in geometry would be if your pipe system passes through a valve, because valves change the geometry of your pipe system and then therefore end up with an energy loss. Another example of a change in geometry would be if your pipe system goes through an increase or a decrease in diameter. It's most likely going to be a decrease, but yeah, that's a change in geometry. So the focus, I would say, of this week's material is not so much to derive equations, although we did do a lot of that on Tuesday, but it is to try to be able to identify these minor loss coefficients. And I'd like to get some practice on how we can identify these minor loss coefficients by trying to solve a simple problem. This problem is not from your textbook, like most of the examples that I try to use. So make sure you take notes so that you can review the solution, so that we can review the solution next week. And while I'm writing this down, I will just give a quick reminder. If you haven't sent me your groups yet for the take-home exam, don't forget to send me your groups, okay? I think by next week, I'm gonna assign randomly to students that haven't had a group yet so that everyone can have a group. I don't recommend that anybody take the exam individually. It's gonna be really hard to solve individually. All right, so let's look at an example. And in this example, I'm gonna give you a system of two reservoirs that are connected. Now this is gonna be a very idealized, very simplified system, just so that we can understand it from I would say a math perspective first. But this idealized system, right, we're gonna be looking at two reservoirs. So we have reservoir number one and reservoir number one is connected to reservoir number two, and that connection passes through a pipe system, or that connection, sorry, is done through a pipe system. Just so I know it looks like I increase the diameter, but let's assume that the diameter of the pipe is constant, okay? So diameter of the pipe is constant. Now, before I start just giving you all this data that you need to solve this problem, I do want you to get a bit of an exercise in how you normally will get problems when you're working as an engineer. Because when I'm asked to solve a problem, when a client calls me to solve some flooding issue or something, they don't say, hey, I want you to solve this flooding issue. Here is the friction factor. Nobody says that, right? Instead, they show me the system, or I visit the field. I visit the site, I look at the system, they tell me where the problem is, and then it's my job to figure out what data I need from that system in order to solve their problem. So I'm just gonna tell you that we have two reservoirs and that are connected through the system. This pipe system, we have a check valve right here. And my question to you is, if the problem, right, if the problem to solve is that you need to ensure that the difference in levels between these two reservoirs is at a certain number. In other words, you want to calculate or determine this difference in water surface elevation H. How do you think you can approach this problem? Like if you were the engineer and you want to ask the client to give you data from these reservoirs, what data would you ask the client to give you? Any ideas?
How many gallons are in each reservoir?
All right, we could ask for the volume of the reservoirs. That's a good option. So we can look at the storage capacity of the reservoirs. That's great. What other data do you think we need?
The length of the pipe?
Okay, length of the pipe. That's a great place to start at as well. Okay, so let's say that they give us the schematic of these pipes, and according to the schematics that were given to us, we have about 20 meters of pipe horizontally. We have about 10 meters of pipe vertically. And let's assume that these distances are from center to center. Okay, so from here all the way to here. And then another 20 meters of pipe horizontally. What other data would you ask from the client? No idea? All right, let's see if we can solve this problem. And I guess when we start solving this problem, we may run into some missing information, okay? So let's go ahead and solve this problem. We want to find this difference in elevation. Now, when you look at a difference in elevation, I would like for you to start thinking, difference in elevation. What does a difference in elevation imply, right? When it comes to fluids, what does a different elevation imply? Any ideas? You have, I don't know, you have two reservoirs connected to each other with a difference in elevation between their surfaces. What do you think is going to happen?
Is there a pressure difference?
Exactly, right? I would say an energy difference, right? You have a difference in elevation, and if the reservoirs are connected, you have a difference in pressure. You also have a difference in potential energy. And you know that if this were the case, then the water levels would want to even out, right? Because you do have more potential energy on the first reservoir than you do on the second reservoir, okay? So if you look at a difference in elevation and you think difference in pressure, difference in potential energy, then your mind should automatically take you to the energy equation. You should say, okay, I want to solve the energy equation. When you are, and I'm not really sure about mechanical engineers because I've done these types of projects, but I've not worked with people that are actually in this field. So, but when you are in civil engineering, which I think some of you are actually civil engineering majors, the energy equation may be referred to as the universal equation. I know some of the old guard calls it the universal equation. And when I say old guard, I really mean my dad, because he's been an engineer for like, what, 40 years or something. So he does call it the universal equation. And the reason why older people call it the universal equation is because the energy equation essentially is pretty much applicable to look at pressure changes, velocity changes, elevation changes, pump changes, turbine changes, and also head loss changes. Whereas other equations that we use in the field, other methods of calculating energy losses are empirical, and they're kind of specific to one type of flow. For example, you'll learn next week, we're going to learn about Manning's equation, but that's specific to uniform open channel flow, right? We're going to learn about the Swami-Dane equation, or sorry, the Hayes and Williams equation that's specific to pressurized pipe flow. So the energy equation, we call it or some people call it the universal equation. And that is because this can apply to any system where we're studying the energy. So we write down the energy equation. We want to use the energy equation. Now, before we even start to try to solve this equation, let's try to get rid of everything that we don't need. First off, this energy equation is for a control volume. So my control volume has to go from somewhere to somewhere. Now, given the data that we already have, it's a little bit limited, right? Because we only asked for volumes, storage volumes, and pipe lengths. We know that our control volume should include, ideally, right, everything that's flowing inside the pipe. And hopefully it should also include the fluid in the reservoir, because in the end, we do want this difference in elevation. And if we want this difference in elevation, we need to include these two water surfaces in our control volume. So what I would do if I were you is I would set my control volume to start at the first reservoir and end at the second reservoir. If we do this, then the energy equation will be correct, because the energy equation has all of the upstream terms on the left, all the downstream terms on the right. Now, given those starting points, what can we start to get rid of in this equation? What don't we need here?
Would you need the velocity?
Okay, so we need velocity. These are our 2 points. What's the velocity at the surface of a reservoir?
0.
Okay. Good. So we have a simpler equation. That's good. And we always want to aim for a simpler equation to solve. What else?
Pump and turbine head.
Okay, good. Do we see a pump here? No. Do we see a turbine here? No. And that's absolutely right. I feel like we can simplify it perhaps a little bit more. Any other ideas? Let's see.
Are both reservoirs open to atmosphere?
Yep. I mean, yeah, this surface marker just means that they're open to the atmosphere.
Okay, so you can cancel out pressure, right?
Okay, that's
P1,
good.
P2.
We have atmospheric pressure on both ends. So really, we can just cancel it out, right? Good. And essentially, we have a pretty easy to solve equation, right? Because now what we have after canceling everything that we don't need is Z1 minus Z2 equals head loss. And within the context of this diagram, what is Z1 minus Z2? What does that represent physically?
That's the H that we're looking for.
Exactly, right? That is the H that we're looking for, okay? So we get that our unknown H can be found by simply finding the head loss. And that's pretty interesting, right? Because that means that our unknown value H essentially corresponds to the loss of energy in the system. And that should make sense, right? From a conservation of energy, that makes perfect sense, right? Because if you have no pressure or kinetic energy, then the loss in energy comes from any energy that is, well, lost, right, as the fluid travels from one reservoir to the other. So that means that all that loss in energy is translated into this system physically as potential energy. Now we mentioned that head loss is divided into two terms, a friction loss term and a minor or component loss term. We also mentioned that friction losses could be found by using the Darcy-Weisbach equation. And we also mentioned that the minor loss term could be found by taking the minor loss coefficient. Now, this minor loss coefficient corresponds to only one element, one component in your system. But if you have multiple components in your system, all you have to do is add up all of those multiple coefficients. So it's not really that big of a difference. You just add all of your coefficients up, okay? So let's see if within the next 5 to 10 minutes, we can actually try to solve this problem. Because we haven't really covered friction losses too much, you can look at the examples from today's video, the video that I am uploading today. So you can see how to calculate friction losses. But for this problem, I'm just going to, in the interest of time, give you the friction loss. So assuming that you did calculate the friction loss and you found it correctly, let's say we got a value of 0.0173 for your friction loss. But then everything else should be stuff that we can either calculate or determine. So we look at the equation, we get our H, our height difference, is equal to, I'm going to factor out my kinetic energy term, but it's equal to friction loss or friction factor times length over diameter plus the sum of all of our minor loss coefficients, and all that multiplied by the kinetic energy head. Do we have friction loss? Yes. Let's say we calculated it. Do we have length? Yes, we do have the length of the pipe, which is the length to which the friction is occurring, because Lauren asked the client to give us that length. Did we ever ask the client for the diameter of the pipe? We didn't. Do you think it's necessary now? It is, okay? So that's why I think it's good to, I mean, you try to find what you need first, but if not, then try to solve it. And as you try to solve it, you'll see that there are some terms that we need, right, that we should have asked for. So on the schematic of the pipe system, we find that the diameter of the pipe is about 10 centimeters. So my diameter is 10 centimeters. Okay, so good, we have our diameter. We need our kinetic energy head. So I'm going to skip this for a second. We need our kinetic energy head. And to get our kinetic energy head, we need our velocity. And that's the velocity of the fluid as it passes through a system. Do we have that velocity? No, right? We don't have it because we didn't ask for it. Okay, so when we're dealing with pipe systems, you'll notice that in engineering, we don't really deal with velocities because any change in diameter changes your velocity. That's not very helpful for us. Instead, we deal in terms of flow rate. Typically, our systems are designed to convey flow at a specific rate. So let's say that this reservoir system is designed to convey flow at a rate of 0.04 cubic meters per second. And that is the information from this design schematics of this reservoir and pipe system. So if our flow rate is 0.04, then do we have enough information to calculate the velocity? Yes, okay, that's good. So now let's go at this last term, the minor loss coefficient. The minor loss coefficient, or in this case, the sum of the minor loss coefficients, corresponds to any place where there is a change in your system. Normally, these are values that you're going to look up. There are tables that have for different types of fittings. You have different coefficients. But instead of giving you those values directly, I do want you to give it a try at trying to identify those places where there are changes in the system. So, Jessica, why don't you try to identify some of those components? Where do you think there are losses in energy in the system?
The bends in the pipe and the check valve.
Okay, we have a loss at the bends. We have a loss at the check valve. That's good. Says Jordan's mic isn't working. Ah, that's a bummer. Lauren, what do you think? Is there anything else or is that everything? I see a shrug. I don't hear anything, but I see a
I
shrug.
think that would be everything.
Okay. Does everybody agree or does somebody think that there's anything else that we're missing? Remember, we're looking for any change in geometry.
What about when the tank turns into the smaller diameter of the pipe?
Exactly, right? When the fluid travels from the pipe, from the tank, from the reservoir into the pipe, we actually have a really big change, right? We have a change in geometry of our system. And of course, we have the same thing when the fluid goes from a pipe to a reservoir. So these are our minor loss components for this particular system. You'll notice that identifying these components is the hardest part of the job. Perhaps not in this class, because in the class, for a test purposes, I have to give you those coefficients. But perhaps when we're dealing with an actual system, identifying them would be pretty much the hardest part. So let's say that you identified them and you used your investigative powers of Google to find the minor loss coefficients for all these fittings. For an entrance, a sharp entrance into a pipe, the minor loss coefficient is typically 0.5. For valves, it really depends on the type of valve, but let's say that for this particular valve, it's 5.7. For bends, it really depends on the type of bend, but let's say that for this type of bend, it's 0.64. And then for instances where flow exits from a small diameter like a pipe into a large diameter like a reservoir or river, it's actually very common to just use a loss coefficient of 1. So given this information, it looks like we have everything we need now to find this loss in potential energy, to find that change in water surface elevation. Since we are starting to get more into the practical side of fluid mechanics, right, we're starting to shy away from our theory, I will try to change a little bit of my language. Typically, when we're talking about engineering terms, I don't really call this the surface or whatever. We just call it the WSE, right? The water surface elevation. So whenever you're looking at design plans, design schematics, you see this WSE term, that just means water surface elevation. So we want to find that change in water surface elevation. It looks like we have everything we need, right? We have that the change in water surface elevation is equal to the friction loss. And just for the sake of this problem, I gave it to you, so 0.0173. We have the length of the pipe, which is 20 meters, 10 meters, 20 meters. So that's 50 meters. We have the diameter of the pipe, which is 10 centimeters. Remember, we want this to be dimensionless, so it has to be 0.1 meters. And then we have the sum of our minor loss coefficients. So we have 0.5 at the entrance, 0.5 or 5.7 at the valve, 0.64 at both elbows, and then 1 at the exit. And all of this, as we know, is multiplied by the kinetic energy head. The kinetic energy head is found by taking the velocity, which we know is flow rate over area. And I know I'm a little bit ahead of time, so let me just try to finish quickly. And the flow rate is calculated, or the velocity is calculated by taking the flow rate, which was 0.04 cubic meters per second, and then dividing it by the area, which is pi over 4 diameter squared. This gives us a velocity of approximately 5.09 meters per second. And that's the velocity that we're going to use to solve this problem. So 5.09 meters per second. All this is squared, divided by 2 times gravitational acceleration, meters per second squared. Good. At this point, I don't think there's anything else we can do other than plug it into a calculator. So I'll let you try it yourself. Try it out yourself, and your final answer should be about 22.6 meters. So before we end today's review session, are there any questions with this material? I know I kind of rushed through this, but there is a lot more detail in the video for the actual class. I just really wanted to do an example like this one, which we didn't get to do in class. But are there any outstanding questions about this material, or do you think it's sort of understandable? I'm going to take those nods as it's understandable. So that's good. Practice, do your homework. You're going to have a lot of problems like this on your homework. And of course, don't hesitate to send me an email if you need any help. All right. So take care. I will see you all